Hi, everybody, and welcome to the Fast Code Seminar. Today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy. I co-chair the organizing committee for the Fast Code Seminar, and I lead community outreach for the larger Fast Code project, of which this seminar is a part. Before Roberto introduces our speaker, I'd like to just take a minute to let you know about the Fast Code Seminar and the larger Fast Code project. I'm going to paste a link to the Fast Code website into the chat. And that's where you can go to learn about the Fast Code project. I'm going to share my screen so that you can see it without having to go to your browser. Okay, I think everybody can see my screen now. Someone will tell me if that's not the case. Fast Code is an open source community dedicated to advancing software performance engineering. And if you, everything's on this side. If you scroll down, you can see the Fast Code Seminar is one of our big featured events. And we can see that here's today's talk, a speedy tour of machine programming. After today's talk, we have another speaker, Rich Voduk, lined up for October. He's at Georgia Tech. Exact topic still to be announced. I'm sure it's going to be awesome. Hopefully as great as today's talk. And I want to acknowledge the seminar organizing committee. If you scroll down past our list of previous seminars, many of which are recorded, you can see the organizing committee, which includes Kuba Lackey and Roberto, who's here, Christian Schultz, Julian Shun, Yihan Sun. And if you want to nominate a speaker for a future Fast Code seminar, we would love to hear from you. So in parallel with the Fast Code seminar, we have lots of other things happening. And one that I particularly want to mention with my last 30 seconds is we have a Fast Code special session at HPEC. And HPEC is a virtual conference that's going to be happening next week. Our special session features 4 panelists, and the discussion is going to be about how to choose good task parallel tools and platforms for your software performance engineering. It's an hour and a half to talk about your questions for how to choose the right platform for what you want to do with discussion with these experts. So we encourage you to check that out. And that's a very brief summary of Fast Code. I want to turn it over to Roberto to introduce our speaker.
All right. So thanks, everybody. So I'm really happy to introduce Justin Gottschlich. Yes. So Justin has a very long record, and I could just, procedurally read through the highlights of his career. We are talking about machine programming research, leading machine programming research at Intel, funding startups, adjunct professor at UPenn at Stanford, 2.64 million subscribers on his Goju Tech Talk YouTube channels, more than 550 videos published. But what I really love about Justin's career is that he has always walked this line that intersects between industry, academia, and education. That's has been his what I felt. It was a particular characteristic of his career. And despite being in industry for most of his time, he has always thought about innovation and lasting impact. And I remember he visited us in Lehigh in computer science in 2018 for a project about persistent memory with some other faculty in my department, Mike Spear. And he talked about machine programming, which is kind of crazy. 2018, that this was like 4 years before LLM and the whole explosion. Now no one can live without that. It's replacing jobs, all the headlines that you want to mention at this point. And Justin was doing that long ago. So I believe Justin has given a lot to the community, and when we were talking about selecting speakers, I thought our community, the Fast Code community, can really enjoy his perspective. Justin, thanks for joining us, and for those of you that want to have a dry run version of this talk, he just published the video went in, I think last day, a dry run of this talk on his YouTube channel with a lot of fun facts about the state of when he was preparing the talk. And also thanks, because I don't know if directly or indirectly you advertise our community in that talk, which is great, and I'm sure Bruce is really excited. So Bruce, if you haven't had a chance, go take a look at the video. And with that, floor is yours. I'll shut up for a very long time. Thanks, Justin.
Wonderful. Thanks so much, Roberto. First, can everyone hear me okay? Okay, wonderful. So thank you so much for the super generous introduction. And before I dive in, I want to thank Bruce and Roberto. We've been working behind the scenes to try to schedule this talk for many months, and they've been super patient with various delays on my end. So deeply appreciate it, and absolutely love what the community is trying to do here. This is something that I personally deeply care about, and I didn't know about fast code. And then when I started to look at what you guys are doing, I noticed that many of my mentors have given talks here on the virtual seminar that you guys are doing. I think I noticed that I'm friends with 3 of the 4 speakers. One of them is Tim Matson, who's actually a longtime collaborator, mentor of mine, and he actually is working with Merly now. So thank you all so much, especially for everyone else for joining today. And feel free to interrupt at any point. I much prefer dynamic conversations than sort of a boring monologue. But don't feel any pressure. If you're nervous, you can drop it in the chat, and I think Bruce will try to intercept those. I also want to share, I'm a little bit under the weather, so my cognition is slightly delayed. So if I seem a little slower than normal, that's probably what it is. But no big deal on that. So we've got about 50 minutes. There's so much to cover here that I can't really give it true attention that it deserves, which is why we're going to call this the speedy tour of machine programming. And at the end of the talk, I'll hopefully share some places where you can find more information. So at a high level, we're going to talk about these various points that I have here. I won't read through these except to mention that really there's going to be sort of 2 segments. The first segment is giving a lot of background on machine programming. As Roberto is mentioning, this is something that I've been working in the space of for probably at least 10 years. And coincidentally, so has Tim Matson. And the first half, right up until this engineering and researching MP, will be kind of laying the foundation of the field and the way that I kind of think about it. And the reason for that is I just want to make sure that many of you who might not have the background in machine programming can see a little bit of the things that we've been working on for quite some time. The second part of this talk will focus principally on, and probably just maybe the last 10 minutes, on some open problems that I think are they have the potential to be very disruptive. I do think that we're living in sort of a golden age of technology, which I think can be very good and it could be very bad. I think that science by itself is neutral, but then how we use it, we can use it for good things, we can use it for maybe not such good things. But what is maybe one of the most exciting things about machine programming to me is that we are on the frontier of sort of creating foundational elements that will launch, I think, our entire civilization forward. And that may sound a bit audacious, but when you start to think about what's actually happening, I think that that's actually sort of at least somewhat reasonable characterization of where we are. So let's dive in. What is machine programming? At the highest level, the way that we think about it, it's the automation of any aspect of software development. I'm going to go over this pretty quickly, but if you were to take my course at the university, you would generally find that I would break it down into these 3 categories: code reasoning, code actions, and then sort of everything else. I want to briefly share why we use the term machine programming and not ML for code, software 2.0, or just something like software automation. As far as ML for code, part of the reason why we spent a long time working collectively between Intel Labs and actually MIT was to help us figure out how to start to reason about this space in a way that made sense and was sort of inclusive. One of the things that I see today that I don't fully love is things like ML for code or AI for code, which seem to indicate or seem to imply that this is just about machine learning. It's just about AI. And I think that couldn't be further from the truth. I think it's far more inclusive. It's sort of a potpourri of many different fields. And part of the reason why I think a lot of machine programming systems are sort of failing today is they are focusing too much just on the shiny new object. As Roberto was saying, too much on the headlines and not necessarily on the stuff that actually matters. And also, this is part of the reason why I love this seminar is I don't think that there's a universe, or at least not the one that I would live in, where performance doesn't matter. It does matter, especially for the pragmatic adoption of any technology. If you only get 1 mile per gallon for your automobile and another automobile is going to get you 50, you're probably going to use the other one. That's efficiency, right? And so similarly, performance is sort of a fundamental first order concern, which we'll get into. So that sort of addresses why we don't call it ML for code, software 2.0. But I also want to mention that this idea of automation of software, I think that it's very important, at least the way I think about machine programming, is there are aspects related to software development. For someone like me that's been doing software dev for 25 years and have written a lot of industrial code, including creating 2 startups and creating things from scratch that are still in production today, what I see is that code is very important, but there's many other aspects to software development that have nothing to do with code. They have to do with sort of the social interaction with a team. They have to do with the specification, problem identification. They have to do with the CI/CD pipeline. So machine programming is intended to cover that entire space. And when we talk about MP systems, we generally are talking about that entire realm of software development, not just code. So now that I've sort of attacked that, let's talk a little bit about why I believe we need machine programming. In my experience in doing software development in industry, largely I've seen that there are at least 2 core problems we run into is that software development tends to be slower than we would like it to be. And also the quality tends to not be as good as it should be. As I mentioned in the video that Roberto was talking about, I've never been on a project and that we've achieved all of our features, we've eliminated all of the bugs, and we've come in on time. So one of the core tenets is to try to make software development faster. Machine programming is principally concerned with this. The other aspect is it's not sufficient in my mind just to move fast. We also need to move fast with grace, with correctness, with quality. And so these are the 2 core things that I think almost any machine programming system that will add provide. And so you might be asking yourself, well, what about all the code assistants that we have today? Depending on who you talk to, some people may argue that these code assistants will make you faster. There are other surveys that show that it seems as though maybe the developers believe in their head that it makes them faster, but then in reality, it actually makes them slower. But regardless of any of those views, one thing that is starting to become very apparent is the quality that we are creating in the software that's being generated from these Gen AI systems is on the decline. And there's numerous studies that are emerging. I have one here, but all you really need to do is either Google some of these or use them, which is something that I've been doing for quite some time. And I've seen that there's a lot of work that we can do to help with this quality. And I want to say that that's part of the reason why I'm giving this talk. That's part of the reason why we created Merly, That's one of the core tenets of machine programming. This is not me just complaining about the state of the world. This is me saying, yes, we have this problem. And that's part of the charter of MP to go out and start to fix this. So hopefully this has motivated you on what machine programming is, why I think it's important. Now we can start to dig in a little bit on sort of the landscape on how at least I think about MP. In 2017 or 18, we jointly wrote this paper with MIT. You can see the authors there that attempted to sort of express the way that we think about this field, which at the time didn't really have any more of a name of Software 2.0, ML for code. And as we worked on this paper, which took us actually a couple years, if you can believe it, this paper is just trying to express the taxonomy and the way to reason about the field. It has no results. That's a long time to spend on a paper for just blueprint. But we felt that it was really necessary because we were seeing a lot of work in the space, but it was a little bit disconnected. So at a high level, the way that I think about machine programming tends to be in these three ways. We think about intention, invention, and adaptation. And intention historically has been the way that we express our views to the machine, usually in the form of code. The invention is usually the construction, at least at a high level, of the data structures and the algorithms that are necessary to at least fulfill that intention. And then the adaptation is to help us evolve that invented solution, however it may be presented, into things that are going to be higher quality in whatever environment it's in. Oftentimes, those quality characteristics are things like improved performance, security, uh, better exercising of the hardware that's available, and also adapting to a hardware software world that is evolving underneath it. Now, I want to share that one of the things that I think is kind of interesting, and I think maybe a demonstration of why the three pillars, at least for me, is important, is when you think about code assistants today, and you think about them in terms of the three pillars, one of the things that I think is very obvious is they seem to work in the space of intention and invention, but they really struggle in this space. This is not only an area that they struggle. As a software engineer that's worked on many projects that are on the order of millions of lines of code, and based on a survey that we just did on GTT, Goju Tech Talk, which Roberto was talking about, what the software engineers generally show is this is actually the hardest problem that we have to deal with in software. It's the iteration, it's the adaptation. And my view of software is this isn't a one-shot process. We aren't creating, as I've mentioned before, the Mona Lisa, where we spend some time, we paint this, and we say, okay, we're done. I believe
Goju,
that.
I'm
Yeah,
sorry to
Bruce.
interrupt. So there's just a key point you're making that you said they struggle in this space, and I think you were pointing at
Oh,
adaptation. So I just wanted to make sure
that's
that
right.
I was,
Yeah.
okay,
Yeah,
got it.
absolutely. Thank you for clarifying that. Yeah, they tend to really struggle in the space of adaptation. And lots of people are reporting this. I've seen this myself. I've been using the code assistants, and while I think that they can be really useful in their current state for rapid prototyping, as well as education for helping people learn syntax of languages, when you try to build world-class software or things that are going to go into production, having the ability to adapt that software in this various landscape, whatever that may be, is critical. And what I think we're seeing is that these systems tend to struggle in that space. Part of the reason why I think that they struggle so much is the foundational elements of relying on language models, as we'll get into in a moment, because of their inherent stochastic nature. That because this isn't a disciplined hard science that is more deterministic, it's really hard to be able to take something and say, this is wrong, now let's make it better. Stochasticity, sort of, you can say this is wrong and it just will try to continue to do various other things. And if you have things that are more deterministic, you can start to learn how to make things better. So there's many more details about this. We just don't have time to go too far afield on this, but hopefully this sort of presents why we wrote this paper, and maybe this helps you in your travels as you start to think about the automation of software development and the various MP systems that you may or may not be building. I want to mention one last thing is that the company that Tim, Taylor and I work at, Merly, our flagship product Mentor, is principally rooted in the space of adaptation. Is that it is meant to work on world-class software and try to iteratively make that better. It does have invention aspects where it will invent solutions and it will leverage language models in sort of tangential ways, auxiliary ways, but the foundational elements of the system are highly deterministic, because I would argue that the majority of hard science is deterministic, and we need that. 1 + 1 is 2, and if it's not, our entire financial systems fail. Our power grids fail. The computers fail, right? And so while I'm actually very excited about neural networks, I've been doing research and teaching neural network architecture since like 2007. I think it's also important to understand where their limitations are. So let's keep going forward, but this hopefully gives you a high-level overview of the roadmap that we have. Now let's get into a little bit of the first principles that I think are critical for machine programming systems. At the top of this list, which coincidentally, this list was created long before I was invited to Fastcode, and it was actually ordered this way because performance is so important to me, that I would argue, again, that any machine programming system that has real value must be performant. And this is part of the reason why I think that LOMs, as I call them, language-only models, are probably doomed to fail because the economics of those models don't make sense. It's unfortunate that we see a lot of hype in the world today. I do see that the world is starting to sort of figure out that, like, wait, it's going to cost $100,000 to just look at this code. Maybe that's not super great. So as we build machine programming systems, first order concern, I would argue, is performance. I want to also share that it's not just that we want these things to be fast because they have value to our customers or our users or for our research. It's also really important as individuals that we can make contributions to the world of science and move things forward. The space that we're living in right now, which is a very strange world, in my view, is the only people I'm aware of that can currently train large language models are big tech. That is handcuffing the entire scientific community for making forward progress. And I think that that is something for us to be cognizant of. Despite all of, if we put all the concerns of where language models fall short, we push all those to the side and say all those things are great. If we just look at our inability to actively contribute to the training process, this should cause us as the scientific community to pause for a moment and ask some fundamental questions. Like, for example, one of the corollaries I would make is, would Linus Torvald and the Linux Foundation ever be able to create Linux if it required $10 million to start up the kernel? I don't think so. And so this is maybe one of the first indicators that the approach that we have here with pure language models is likely to put us in a very weird position. And I'm not sure that we necessarily want to be there. So that's point one. The second, I think, principle for machine programming systems is that they're deterministic, largely. Now, I think something that is often overlooked about this is, first, I've been teaching neural networks literally, I think, since I was a grad student at University of Colorado Boulder back in maybe 2007. And I stayed on as an adjunct to do that. Then, as Roberto's mentioning, I went to University of Pennsylvania, and now I'm over in NorCal. And the entire time I've been teaching AI, machine learning, but my heart has largely been in neural networks. So I think that I would argue I understand them fairly well. One of the core issues with neural nets is that they are inherently stochastic. And we can get into a super deep debate with all of you super smart people on why that is, but let's just get to the foundational element that without randomization on the initialization of the weights, then you lose the ability to have wider ranges of convergence properties. And even if you seed things based on some predetermined value that gives you a correct neural network as your output, that seed may not work as you try to train that neural network for larger things. So why is this so important? Well, first, most hard science is deterministic, and it's critical for iterative refinement. So let's not even think about the users of these machine programming systems. Let's think about the machine programming systems and how we want to make them better. Okay. This is my phone. All right. This is my Samsung Fold phone. The first version of the Samsung Fold phone was not very good. This is version number 6, I think. When you have determinism, you can do iterative refinement. Because large language models are inherently stochastic, they inhibit the ability for any team, no matter what their intentions are, to be able to iteratively refine them and make them better, which is part of the reason why I think you see things like GPT-5 doing worse. It's not that OpenAI isn't trying to make it great. They are. It's just that they're dealing largely with a stochastic system that is out of their control. This should be a wake-up call, I think, to anyone that is really saying, oh, language models are the future. If you're working in the space of soft science, if you're working in a space where things are more subjective, I think language models can be a fantastic solution. But if you're working in spaces that they tend to be more objective, they tend to be more deterministic, like most software systems, not all. I understand distributed systems, parallel systems have degrees of non-determinism in them, but oftentimes that non-determinism is non-deterministic in latency, not in outcome. That's actually a really important distinction. So this is part of the reason why determinism is the second most important property, and you can build AI systems that are deterministic. We have done it at Merly. Our system is foundationally all machine learned, but it's just deterministic. It basically gives you the same answer every time. This allows us to make it better and better and better. And if you've been following the progress of the company, what you may have seen is our first attempt with building Mentor, it was terrible. It was 70% false positives. Our false positives now, as far as identifying things, is almost 0%. This is what determinism often gets you. And what's super interesting about this, as far as I'm concerned with the code assistants, is anyone that's done a serious degree of software development knows that iterative refinement is not only the foundation to science and the scientific method, it's how we build software. It's why we have Windows 11. It's not just Windows, we're done. Or we have numerous versions of Linux. So I think I've beaten the second topic. Let's go to the next one. The next property is we want these machine programming systems often to be as objective as they can be. Now, I want to be super clear. In the world of reality, having things be perfectly objective is very hard. It's mostly a nines problem. And any machine learning system, at least to my knowledge, it's probabilistic in nature. So any sort of inference that you might give that is going to be out of distribution for your actual training or your testing data, you can't say definitively that it will be 100% objective. But I do think that we can strive toward this. And this is a really important property for hard science systems. It's distinctly different from determinism. So for example, you can have something that's deterministically wrong. And you can also then, when you have that determinism, you can try to make it correct. And so this objectivity is an additional piece. I would argue that these are sort of like the 3 fundamental characteristics or principles for most machine programming systems. And in fact, at the university, this is sort of the way that I teach this. The last 2, I think, are more related to pragmatic value being used in the real world.
Goju, we have a
yeah.
question.
Okay, yeah.
From Mike. Aren't these 3 pillars, intention, invention, adaptation, true for any human endeavor? And if you make intention and invention too easy, that is, without too much thought, you may solidify a solution that thwarts adaptation. Perhaps if
Yeah.
you make adaptability part of intention, that might help? Question mark.
Yeah, so I love this question. I actually, to be honest, I don't know that I've ever thought about it like this, but after this talk, I'm going to think about this more deeply. My knee jerk is this is the way that we actually think about these types of things at Merly. And in my personal life is I try to think about it as I have an intention to do something, I'll try to come up with a high level answer. But then I know, having failed thousands of times, that answer is probably not right, and I'm going to need to iterate. So, and thus the adaptation. I would have to think about it more deeply, but my knee jerk is I think that there's whoever is making this comment is directionally correct. I think that there's a lot to be learned here, and I love the comment. Thank you for that. Okay, cool. So the last two properties on the first principles. By the way, this is not exhaustive in any way, but these are just the things that I think are really critical. That what I've seen today in today's world of a lot of hype with language models, these are some of the core properties that are overlooked. And many of these systems, if you look at many of the code assistants, they all suffer from not being able to have enough sophistication in these areas. The next area is being able to support machine programming systems running entirely on-prem. And this part, I think, for the practical application of MP systems for institutions that have code IP is paramount. It's actually highly amusing to me that uh, I'm not going to try to throw anybody on the bus, but it's just weird that some big trillion-dollar company believes that everyone will send their IP code to them, yet the inverse would be a non-starter for them. One of the companies that we're working with, it's this fruit company out of Cupertino. They're very particular about me not using their specific name, so I won't. But one of the reasons why they're working with us is they love the fact that Mentor can run on-prem. And if you look at language models, and specifically the large kind, this is an issue, I think, for smaller companies or companies with code IP. I'm not ruling out that small language models can have benefit here. I think that they absolutely can, but that's an important distinction and sort of recharacterization of their capabilities in this smaller space. We actually at Merly are using not only our own homegrown AI, but also small language models to help us support this. So the way that it works, at least in the systems that we're building, and these are not just research systems, but also practical systems, is they work in three spaces. They work entirely on-prem, they work on the cloud, or they work with both. And various different places often require that hybrid solution. It's sort of an amazing place that we're in today, where the cloud solution is the easiest in some sense. Taylor Dolezal, my co-founder at Merly, he's on this call. He was the head of ecosystem at Cloud Native Computing Foundation, so he knows a lot about Kubernetes, and we really are very sophisticated. That's great that we have all that cloud support. On the other hand, there are really important times where we want to be on-prem and we can close off the world. There's also really interesting emerging cases that I'm seeing in my discussions with folks like Qualcomm and Microsoft and Google, that on device, not just on-prem, but on device is also very important for inference. And there's a number of reasons why this is the case, but as we see with large transformer-based systems, this might not be possible. We can continue to invent. Like part of what I'm super excited about our community, the machine programming community at large, as well as Fast Code, is that we are sort of the scientists and scholars that are driving the invention of these new AI systems forward. And I think that's one of the things we need to continue to do, is to push the boundaries and rethink some of these fundamentals and continue to come up with new solutions. The last point is that there's more to the software systems than just code. And one of the things that helped us identify the XC-utils backdoor Linux hack is that we reason about contributors' behavior over the lifetime of the repo, and that gives us insight into anomalous behaviors in the community. I think that when we move forward on MP systems, again, going back to the point that I was trying to make earlier, how there's this other space, this would be an example of that it's not always just code. There are very deep social ramifications here. I may have an unreasonable amount of background in sociology. My ex-wife, who I was married to for about 15 years, she's a world-class scholar in sociology. So she's taught me a ton of things. I don't know a fraction of what she knows, but enough to know that this is something that I think really matters. And it's something that us as computer scientists, we sometimes overlook, but it's actually can be very important as we're building these systems. Excellent. I'm going to keep powering through. Now, if we look at machine programming from this 30,000 foot view, and we know that we've got this machine learning component, I would argue that there are at least 3 different areas that are fundamental to MP systems to make them practical. And I want to just quickly talk about these 3 here. The machine learning part, I think that we probably all know and love, and we spent some time on that. What I am seeing in the world today, especially in sort of the hypey VC world and startup space, is there's a lot of attention on this, which I get. It's a shiny new toy and it's exciting. But without deep understanding of these 3 areas, I think that it can be hard to add real value for these machine programming systems. So let me just give you a couple examples. Part of the reason why Mentor can run so efficiently and on-prem and do analysis of potentially like a million lines of code in a minute on commodity hardware is we don't reason about code. We do not reason directly about the code. Instead, we have built over a dozen intermediate representations that tease out the semantic information that is hidden behind the syntax. And what it does is it creates a compression, a condensing of that information. And what happens is when we can compress the code information into like 100x smaller space, it allows us to be able to reason about things in a much faster way. Without a deep understanding of programming languages, you may not know how to do this. One simple example is if we look at things like for loops, while loops, do while loops, all of those at a very high level, it's just the concept of iteration. And so we could remap that as iteration. What that can potentially do is rather than requiring you to have these disjoint grammatical representations, you can unify them, and that can reduce your space. That's just one of hundreds of examples that you can do when you deeply understand programming languages and you're building MP systems. The next piece is software engineering. I would argue that if you don't have a deep understanding of software engineering, it may be very challenging to build an MP system that has value because you may be solving the wrong problems. So for example, I would argue, as I think Linus Torvalds has, that humans that are writing software, we've been able to write code for a long time just fine, as well as really bad code. What we really struggle with, though, is writing really high quality code. Even me that's written maybe millions of lines of code, I still don't get it right. And so part of the reason why Mentor is focused on in code quality is that I know that even the veterans still get this wrong. And I would argue that if you are building an MP system and you spend time deeply understanding what the core challenges of software engineering really are, you will likely build an MP system that has true value. Another example of that is something like Git. I also see that there's this really interesting parallel between things that have the appearance of potentially be boring and have value. Is I sort of see that if it's shiny, if it's flashy, and it's very headliney, it seems as though there's some correlation to and maybe not having super incredible value, at least not beyond a flash in the pan. But things that potentially are maybe a little quieter, a little more boring, but are really focused on solving something that's really important, I think those can actually help us in the long term. I think that if you were to ask people today if they know what Git is, I think almost everyone that's done software would say that it is. But if we think about it, like, how is it that a version control system is changing the world? It's such a silly, boring problem. Well, it's fundamental to software engineering. And the truth is, before Git, for those of us that are working this space, it was it was not a great space. We would have things like the source control system would eat our entire database. That actually happened to me in production code for Notica when I was first starting out. Never in a million years did I think that Microsoft's Visual SourceSafe would destroy my entire repo, and it did, right? So there's something beautiful here, I think, about looking at software engineering and asking the hard questions of what actually matters? What do people actually spend their time on? Is it writing a bunch of superficial code, or is it things like trying to understand stuff? Maybe even have a system that just explains very complex code, or things like transpilation, transpiling systems from COBOL to Python, or what have you. Maybe that's a bad example. But so those are these two. The last domain I want to share is related to systems. And this again goes back to performance, is that you can have the best machine programming system in the world, but if it's costing tens of millions of dollars to run inference, it may be hard for the average person to use this. What's great about the fast code folks is I suspect this is sort of your bread and butter. And at least based on what I'm seeing, they're oftentimes today, for many of the early machine programming systems that I see, there's an overemphasis on this space and very little emphasis on this space. And with a small amount of effort, at least a small amount for us, we can probably 10x or potentially 100x these systems. That said, I want to share that it's not always the case. Sometimes we actually have to have a complete departure from the architecture that we're using to get a solution that's going to be performant. And in fact, that's part of the reason why we created the Mentor Merly's AI system is my experience with neural networks. The way that I describe it is it just has too much computational friction. I like to draw the analogy of it's like trying to take an automobile from the West Coast to the East Coast, and you are going through all these cities, and you have to hit all these various points. Maybe a more efficient way is just take an airplane. But take an airplane will require you to architect a fundamentally different solution. It's not about speeding up the automobile. If you do that, it may fly off the street, right? It's just, then that's no good. So you may have to, some of these systems may actually require you to fully re-architect them at their core. Okay, I have one more slide on the background, and then maybe that'll be a great time to pause for any questions or anything. So I'll just try to speed run this. The last slide on the 4 domains, as I was mentioning, this is not meant to be exhaustive. It's just the things that I think are highly important from my perspective on MP. This is meant to sort of give us, I think, a more broad view of how to build MP systems that I think is maybe a reminder that maybe some of the best solutions we can build are a hybrid solution of things. As many of you know, I'm a huge fan of Armando Solar-Lozama's work out of MIT, and he's been working in the space, I believe, of neurosymbolic systems for a while. In fact, Mentor system is, one way that you could argue it is it's like a neurosymbolic, except it's not necessarily neural. It's more general than that. The way that I reason about these two spaces is that you can build MP systems from a stats-based solution using machine learning, or you can do it how we've done it historically, which is more rules-based. But you can also do it using both simultaneously. And neurosymbolic is one example of that. The neural is the neural network stats part, and the symbolic is the rules-based part. And I find that this can often be very helpful when you're trying to do things like improve the objectivity or the determinism of the system. The probabilistic side maybe doesn't get you there, but it helps you generalize and then work at scale, which can be much harder if you have rules only for really small sets of problems. But the rules can really help ground the stat-based systems when you need to improve their fidelity for some specific space. So my view is oftentimes when you're doing engineering or research of these systems, I found that some of the most interesting ones, they're not just machine learning, and they're also not just another intermediate representation or a formal method. It's a fusion of things like what Armando has been doing with his advances in Sketch, for example, which principally started out actually, I think, on the rule side, and then he advanced it in the stats-based side. I think Alvin Chung out of Berkeley is doing similar stuff with his verified lifting and MetaLift stuff. And Merly is doing also similar things, is that we have invented new AI algorithms that's on the stat-based, but we've also invented new IRs on the rules-based. And we use them in tandem together to solve this problem potentially in a novel way. So at this point, I'm done with the first larger section, and the last 15 minutes are more just exploring open problems. I want to pause for any questions or comments.
So Justin, quick question. For our community, Fast Code advocates for performance engineering, freshman level or sophomore level. From the beginning, students need to understand writing code is not just about making it work, but it's also making it work fast. What do you think is the role? Again, intersection between education. I mean, many of the things that you said are from a standpoint of somebody that is an expert. We are expert on writing and thinking about code. How you think about students that are approaching performance engineering, software engineering, how should they see these tools? Should they still aim to become experts on the deterministic world and then embrace the stochastic world, or they should be started thinking in this hybrid mode that you were talking about, or something else?
Yeah, that's a fantastic question, Roberto. And just so you know, I being at the university for a while, and I know many of you are also professors and are teaching, and you're seeing a similar thing, which is computer science as we know it, I think, is changing and evolving. And some of that I think is really good, and some of that I don't love as much. And so one of the things that I think is happening is Python is sort of becoming in like a vehicle to teach computer science, at least at sort of the freshman level, right? And I think that's wonderful, as long as we still are teaching performance engineering. And so, for example, what I do, and again, this doesn't exactly get at your question. I'll probably have to think about this quite a bit offline. But for my class, so I only teach at the graduate level, so it's just master's and doctorate students, which again is not what you're asking. But I make it mandatory that people are writing their prototype systems in basically C and C++. So I'm letting them know right out of the gate that you're going to have to go lower. And all the examples that I use are C++ or C. And what I find is that at least at Stanford, the students that take my course at the graduate level, they do tend to have a far larger familiarity with Python for sure, and other higher level languages like JavaScript. But I think that if we use it as a funnel, that we start basically saying, look, there are perfectly good reasons to use Python for prototyping and high level stuff that's going to be internal only, 1,000%. I use it all the time for things like that. But as we build things like Linux or Git or Mentor or real world MP systems, Python's generally not going to cut it in its current form. Now, I know that a lot of people are like probably chomping at the bit here saying, no, I'm working on these optimizations to make Python faster. And I love that. I think that's super great. And I do think that we need that because I think that there's probably going to be a large majority of people that are still writing Python and JavaScript. But minimally, I think that there probably needs to be something fundamental in computer science departments, in the world where we have some kind of dedication to this performance engineering, if for no other reason than just to teach the principles. I would kind of liken it to like calculus, is that we make these courses fundamentally required. And it doesn't mean you have to be an expert, but it minimally means that you need to understand the principles. So then when you get into hot water, which you will likely get into if you get deep in these systems, that you can get yourself out of it because you understand at least things like how to build your own memory manager, or the costs of garbage collection and the non-deterministic invocations that GCs can cause, and understanding live lock things that happen in parallel. So it's like I kind of think of there could be some undergraduate course that's sort of like performance engineering that is meant as a potpourri, as basically saying, look, we're not saying that everybody has to be an expert in this, but you minimally should understand the principles so that you can then help get yourself out of hot water when you get into it. I realize that doesn't answer your question exactly,
No, but
Roberto.
and I like it. The spirit is actually what we're advocating, focusing on the principles more. I think that's what there is right now, right? So focusing on the principles gives the students and in general everybody a little bit more than focusing on the details, because the details they can probably get them through LLMs or other tools, but the principles are the hardest part. Thanks.
Exactly. And in fact, I have a slide deck that I show when I teach, and I show this pyramid of learning. And near the top are concepts, and at the very bottom is sort of memorization. And I make it very clear to students, these lower levels, I don't teach, because you guys can do this on your own and learn those details like you're mentioning. But I will teach the high level, because what I can provide, I think, and what all of us can provide, is we can teach them those concepts. And as long as they conceptually understand, they can likely derive the answer in whatever space that is. So I love this point, and we should definitely discuss it more offline.
Thank you.
Excellent. Okay, so I've got just a couple slides left, and now we're going to talk a little bit more about the forefront of what maybe in front of us for machine programming. And I want to start by saying that I believe we're in this space of repioneering the 7-year-old problem of compilers. And the way that I think about it is there are principally these two sides of MP outside of everything else. There's code reasoning and there's code action. And you can see parallels with any machine learning system. Is there's the training and then there's the inference. What's really important here is, I think we all know, if you don't spend a lot of time training your system to do really well, the inference is always going to be subpar, right? A similar thing is sort of fundamental to machine programming. Code reasoning is, in my mind, the precursor to code actions. And so what we really need to be doing, especially as thought leaders in industry and academia, is to make sure that the emphasis is not lost on code reasoning. I see a ton of things on Gen AI, which is really in the code action space, and not enough on the code reasoning part, which I think is the key to unlocking the future. And so one of the things that the way I think about this is that while our historical compiler work has given us massive performance gains, as well as things like Dennard scaling and Moore's law, we can go much further now that we have machine learning systems that can do reasoning that's much deeper. And we, rather than doing simple performance or maybe simple is not the right word, but rather than doing optimizations that might only get you a 10%, 20% performance gain using things like dead code elimination or loop unrolling or whatever, what if we could do full algorithmic rewrites, that we could change the entire complexity class of these algorithms for O of n squared to O of n or something like that? And I think that that is where we are now. And I think that with these MP systems, we can start to reason at a much deeper level. And that, I think, is one of the core open problems in machine programming. The way that I teach it today, and by the way, this is, I don't think that this is right in any stretch of the imagination. This is just a sketch of the way that I try to teach it. My students are helping me level this up. All of you can tell me this is wrong, and I agree with you already. But the way that I think about this is something like this. At the basic level, we have code syntax, and this is our traditional analysis: static, dynamic, hybrid, what have you. Then beyond that, at a more sophisticated level, there's the semantics. This is sort of what it means in terms of what the code is doing. Beyond that, I think, is code intention. This is what it intends to do. The fundamental difference between semantics and intention, in my mind, is that intention can tease out things that are not said, that are absent. They can tell you about information that is not necessarily there. And this may seem like, well, how could you do this in code? One of the ways that you can do this is through repository time dilation. You can do temporal reasoning over the lifetime of the repository, and you can start to see intentionality in changes that are happening. And what people are mostly doing today, probably because it's just easier, is they just look at the current state of the code. But we have systems that are keeping track of all this stuff. I think that the future is this. And we need these systems to be hyper fast, because rather than reasoning about just 7 million lines of code, which is Kubernetes, if we do full temporal dilation, it's 700 million lines of code, right? So this thing needs to be extremely fast to be able to reason at the intention level. So I would argue the understanding is maybe the next level, understanding that I'm giving you instructions to go buy peanut butter and jelly. Comprehension would be, did you also mean to add bread? Notice that if I just give the grocery list of peanut butter and jelly, I don't mention, but the understanding is understanding what I'm asking. Comprehension is saying, oh, no, I see the pieces that are missing, right? So this is, I think, one of the most important open problems, and we're working deeply on this, and I would love to collaborate with all of you on this. Just for the point of completeness, I have this thing about code action, which I think is mostly exhaustive. It fundamentally is code addition, code change, and code removal. A lot of the Gen AI systems work in this space, and this space, I think, is one of the easiest. This space, I think, is significantly harder, as we were discussing before. This is also supremely hard, figuring out what code you can remove without necessarily breaking things. And these are real problems that we're seeing with our industry partners. So I'm almost out of time. I want to quickly share that if you enjoyed this talk and you'd like to learn more, you can do that in a variety of ways. One, if you're in NorCal, you can take my class. Unfortunately, I had to cancel it for the fall. This is the first time I've canceled it in 4 years just because stuff's going on with Merly, but I may be teaching it in the spring. So if you're in NorCal, and even if you don't attend this uni, just ping me and you can sit in for free. You can also go to our website and download Mentor for free. And if you ping us and say, I'm an academic or I'm open source, we'll give you an unlimited license to use it however long you want. Or if you want more informal discussions that maybe don't have as much scientific taxonomy like this talk, more casual, sip your tea, coffee, whiskey, whatever have you, check out GTT, as Roberto was mentioning. And last but not least, I want to share that this picture is actually created from my vibe coding system that I created sort of actively in the GTT community. I demonstrated how you could build these things, how they can be useful as toys. And for my thumbnail generator, I think it functions fantastically. So the parting comment is code assistants, I think, still do have value. I'm not saying that they don't. Just maybe going to need some work for them to be production ready, but you can still generate fun things like this. So with that, thank you so much.
Thank you, Justin. This was fantastic. Bruce.
Yes, thank you, Goju. And I think we can, is there any final question or two? It's the top of the hour. But I'm happy to take, if anybody's got kind of a good closing question to pose to our speaker.
And if not, I'm more than happy to answer any questions over email or in the comment section on GTT.
Thank you, Justin. I'm seeing a question in the chat about, will the video be made available anywhere? Yes, absolutely. I'm going to be posting this on the Fast Code site, right where all the other Fast Code seminar presentations are. And that'll be up probably tomorrow.
Bruce, I want to just I want to thank you, Justin, one more time, and share something that I really believe. CS and especially coding tends to be a little under attack these days, thinking that LLMs are going to replace and do everything. We need more people like Justin that they know the technology and they know the real world and then advocate for understanding why the core principle or CS are what's actually still in great need for the future of products, or for the future of the society as we know, to keep developing high quality code that goes fast and it's understandable and it's deterministic when it's needed and it's correct for the highest and more elegant definition of it. So thanks, Justin.
Yeah, no, thank you, Roberto. And just to add to that, that's actually part of the reason why we created GTT is being in Silicon Valley, I don't necessarily love the game. I just have to play the game. But we felt like there's so much hype that we needed to do something to sort of level things out. And I'm very much of your mindset. And I want to share that I see that the world is really kind of seeing the emperor's new clothes. And I love it. I love that. There's actually an article, I think just last week, that MIT came out with that 95% of the AI projects are failing. And I think that's a good example of how AI has tremendous value, but we should really try to limit the hype.
Super,
Thanks
thank
again. Thanks again, Goju. Thank you, Roberto. I am very happy for everyone to be a part of the seminar, and I'm going to wrap it up. So I'll post the recording tomorrow, and mark your calendars again. Next week is HPEC. We have a special session Monday, and there's Rich Voduk as our speaker in October. Thanks again, everybody.
Wonderful.
Bye.
Bye. Thank
Great.
you, everybody.
Thank you guys so much.